In the first two examples in this section, we looked at these polynomial sorts of areas between, or the area between curves that were polynomials. But what if we have a transcendental sort of function? And that's what we're going to look at. So let's find the area bound by y equals e to the x and y equals e to the negative x plus 3. To start this, what we're going to do is we're going to graph it. Right? So we're going to go ahead, and by the way, it's also bound by x equals 0, which is the same thing as the y-axis, by the way. Okay, so whenever you see x equals 0, that's our y-axis. And so if we go through and we graph these, so we have e to the x, and then we have 4e to the negative x plus 3. Right? And then I'm going to scroll out a little bit. And remember, we're also bound by the y-axis. This is the area that we're looking at. Okay, now notice that the point of intersection is right about here. All right, so it's not necessarily a nice one. All right, remember the other examples, we have like 0, 1, 3, 2, negative 2. This one sort of falls, it's not even like a 1.5. So we're probably going to need algebraic methods to be able to verify what the limits of integration are. But anyway, if we sketch the graph as best as we can, all right, on our plane, then we know what e to the x looks like. It looks like this. And then e to the negative x plus 3 is going to look something like this. And this is the area that we're looking for. All right. And we know that the point falls somewhere between like 1 and 2. All right. So this is just a really rudimentary sketch of this. However, if we look at this sketch, it's much more accurate. Right. So to find the points of intersection, we're going to set the functions equal to one another. And that means that e to the x is going to be equal to 4e to the negative x plus 3. Now, this type of equation isn't necessarily the easiest one to try to solve. First of all, because we have an e to the x, but moreover, we have an e to the negative x. What we're going to do with this is we're going to multiply everything through by e to the x. Because what that'll do is when we multiply this e to the x by the e to the negative x, we're just going to use our algebra rules. And e to the x times e to the negative x is actually going to turn into e to the x minus x, which is e to the 0, which is 1. So it would actually get rid of almost all those e's, right? So multiplying all the terms inside the equation by e to the x, we get e to the 2x is equal to 4 plus 3e to the x. Now, it doesn't look like it, but this is actually a factorable sort of equation that we can try to solve. So what I'm going to do is I'm going to set everything to 0, and I'm going to write it like this. E to the 2x minus 3e to the x minus 4 equals 0. And notice that if I wanted to factor this, it's not a trinomial, but it's a form of a trinomial. To build e to the 2x, I have e to the x and e to the x. Two numbers that multiply to be -4, but add to -3 would be -4 and +1. All right. Of course, if you don't trust me, you can FOIL it out. Okay. And so that means that the two solutions are generated when e to the x plus 1 is 0 and e to the x minus 4 is equal to 0. Or e to the x equals -1, e to the x equals 4. And to undo an ln or an e, we're going to take the natural log of both sides. So ln of e to the x equals ln of -1. Ln's and e's go away. So we get x equals ln of -1, which is not a real solution. However, over here, ln of e to the x equals ln of 4, and ln's and e's cancel out. X is equal to the ln of 4. All right. And so this value back on the graph right here looks like it should be like ln of 4 for x. All right. Now, the question is, does it make any sense? And so what we could do is we could just go to our friend Wolfram Alpha, and we could just type in, what the natural log of 4 is. All right. So ln of 4 is 1.386. Now, if we go back to our graph, all right, clearly this point of intersection right about here is between 1 and 2, closer to 1. If I kept zooming in on the intersection point, You can notice right here, it's between 1.3 and 1.4, and I could keep zooming in if I chose to. So notice it's like 1.38. So it certainly makes sense that ln of 4 is going to be the point of intersection. The lower bound is going to be 0, okay? Because remember, our graph starts right here when x is equal to 0. And so now what we can do is we can set up an integral to represent this area. Okay, so this is our function e to the x, the lower bound, and then the upper bound is going to be y equals e to the minus x plus, or y equals 4 e to the minus x plus 3. And so if we go through and set up an integral for this, our area is going to be equal to the integral from 0 to natural log of 4. The top function is 4e to the minus x plus 3. The bottom function is e to the x, or the lower function. Okay, so that's our setup for our integral. To be able to evaluate this is actually pretty easy. The only thing that we have to remember is that when we're taking the antiderivative of e to the negative x, we have to divide by -1. Okay, so remember that trick. If you have a function that's linear, that's composite, it's the opposite of the chain rule for derivatives, right? So this is going to be equal to 4e to the negative x over -1 plus 3x minus e to the x. So minus e to the x, ranging from 0 to ln 4. All right, now, unfortunately, 0 doesn't wipe out all the terms, okay? On occasion, 0 will wipe out the terms, all right, like polynomials, but it doesn't this case. So let's substitute ln 4, all right? So we get negative 4 e to the minus ln 4 plus 3 ln 4 minus e to the ln of 4. So that's our upper bound. And then for our lower bound, it's going to be negative 4 e to the negative 0 plus 3 times 0 minus e to the 0. All right, now, one thing that we have to remember is that e's and ln's undo each other. All right, but we have to be really careful with this because there is a rule of algebra that we need to make sure that we follow. All right, so one of the rules of algebra says, especially for logarithms, is that if there's a coefficient, what you can do in front of a logarithm, you can move it as the exponent, okay? And so just for this term, we have to do this, okay? So when we simplify this, this is going to be negative 4e ln 4 to the minus 1 plus 3 ln 4. We know that e's and ln's cancel out, so this is going to be minus 4. And then minus negative 4, because e to the 0 is 1. This goes to 0, and this is going to be a negative 1. All right, so this is going to be minus 1. Okay. And what we end up with, this actually works out really nicely at this point. Okay, so this is going to be negative 4 times 4 to the negative 1 plus 3 ln 4 minus 4 plus 5, right? And so after all that's said and done, this is actually really cool because we know that 4 to the negative 1 times 4 is just going to cancel out to be negative 1, all right? And if you don't trust me on that, another way to think about that is 4 to the negative 1 can be written as negative 4 over 4, which could just work out to be 1, negative 1 in this case. So we get negative 1 plus 3 ln 4 minus 4 plus 5. So we should end up with 3 ln's of 4. Another way to write this is ln of 4 to the third, or ln of 64. All right. Now, of course, if we don't like the way that this answer looks, we should always go into Wolfram Alpha to make sure that when we try to evaluate it, we get something that at least looks something like ln of 64. So I'm going to go ahead in Wolfram Alpha just to check my answer, and I'm going to integrate. And I'm going to integrate our 4e to the minus x plus 3 minus e to the x. All right, and remember that ranged from 0 until ln of 4. All right, so let's see what we get here. All right, and it gives us log 64. Remember, in Wolfram Alpha, log and ln mean the same thing. If you don't trust that answer, check this. You get 4.1589. If you went in here and you just did ln of 64, 4.1589. Okay, so it's the same number no matter what. So it seems like we got the right answer for this. Okay, all right, so we're going to do one more example after we're done. We're going to do one more example after this video, and we're going to take a look at what happens when we have a radical sort of expression in here. Okay, so that'll be our last one with respect to being able to look at algebra function or algebraic expressions and transcendentals for areas in terms of x. And then we're going to take a look at what happens when we're trying to find the area in terms of y.